Hello and welcome back to the series on calculus. Now, this video is going to be a bit of a supplementary video to the previous one because I feel like I didn't have enough examples in it. So I'm going to go through 4 common limit examples and we're going to figure out what they evaluate to and if they evaluate at all. So let's get right into it. A here, we can see that on the denominator, I'm going to highlight, has an x term just by itself. And when we approach 0 with that x term, that bottom is going to get closer and closer to 0, meaning we're going to end up dividing by 0, which, as we discussed, is totally violating arithmetic. On the top, though, when x approaches 0, we get 3 cubed minus 27. And 3 cubed is 27. 27 minus 27, 0. So the top approaches 0, and so does the bottom. So let's figure out what's really happening here when we get into it. So, first place you want to start is you want to get these terms up here, this cube term, you want to get it expanded. So that way we're not dealing with that as a standalone term. And we can see what happens from there. So, we're going to just do this separately. 3 plus x. And we're going to write it out 3 times because we are cubing it. Next time I confront a power like this, though, something, I'm going to use a shorthand. This is going to be the first time and last time I'm going to write out an expansion like this and do it. So let's go ahead and compute the first one. So we're going to have 3 times 3 is 9. 3 times x is 3x plus this 3 times x, which is going to be 6x there. And then we have the last combination, x times x, which gives us x squared times 3 plus x. And then when we do the next idea, 9 times 3 is going to be 27. I don't need brackets anymore. Whoops. It's going to be 27. 9 times x is going to be 9x. 6x times 3, 18x. 6x times x. 6x squared, yada yada, 3x squared, and then x cubed. Let's group together our like terms, put the x cubed up front. X cubed plus 9x squared plus 27x plus 27 is going to be this term right there. So let's go ahead and use that term in our limit now. So the limit as x approaches 0 of x cubed plus 9x squared plus 27x plus 27 minus 27, because that was in the original limit, all divided by x. So what we notice right away is that this 27 and this 27 cancel out. And when I write down the next layer of the limit, just implied that the limit sign's still there for now. I'm not going to write it in. We're going to see that we're going to have x squared plus 9x, x cubed plus 9x squared plus 27x all divided through by x. And hey, did you look at that? That top term all has a common factor of x. So let's divide it out. X times x squared plus 9x plus 27. Divided through by x. And hey, that's going to cancel out. So this leaves us now with x squared. I'm going to write the limit out front now because we're going to use it. Limit as x approaches 0 for x squared plus 9x plus 27. And because we don't have any denominators that approach 0, we could simply substitute in 0 into each of these terms. So 0 times anything is still 0, and leaves us with our final limit of 27. So this limit up here, we know, equals 27. All right, let's move on to the next one. We have right here the limit as x approaches infinity for x squared plus 3x plus 2 on top, divided by 2x minus 2. Let's look at the behavior of the top functions. So when I square a number, it makes it bigger. And when I multiply through by a number, it also makes it bigger. So as x approaches infinity, the top term also keeps getting bigger. But notice the bottom term also keeps getting bigger. You know, I plug in 5 into that equation on the bottom. 2 times 5 is 10 minus 2, that's 8. And then if I plugged in 10, 2 times 9 is 20 minus 2, that's 18. It gets bigger too. So let's take a look at what happens when we take this sort of infinity divided by infinity scenario. Which one's greater? Are they going to equal out to some limit? Is it just going to tend off to infinity, tend off to 0? Let's see what happens. So when we approach one of these, instead of doing the substitution method that I showed you, which is very useful, and you can use that for a whole whack load of other limits, let's try a different approach where we're going to take this leading term right here, this x squared, and we're going to multiply the top by 1 over x squared, and we're going to multiply the bottom by 1 over x squared. And what you're going to notice when we do that, when x approaches infinity, is that x squared times that x squared term is going to leave us with 1. This is going to leave us with 3 over x, because x times 1 over x is 1, times 1 over x again is 1 over x, so it leaves us with the 3 over x plus 2 over x squared. Now on the bottom, we're going to have 2 over x minus 2 over x squared. Some of that first equation is sort of leaking in now, but it's alright, we'll ignore it. Now what happens when we take the limit as x approaches infinity for each of these terms individually, we could see that on top, this term's going to approach 0 as x gets bigger and bigger, like we saw before. This term's going to approach 0 as x squared gets bigger. This term's going to get closer and closer to 0. This term right here is going to approach 0. And this term right here is going to approach 0. And what we end up with isn't a 0 divided by 0 scenario, not even an infinity divided by infinity scenario. We end up with a 1 divided by 0, which is totally prohibited. So in this example, we normally say, therefore, the limit doesn't exist. The limit does not exist. But what we actually know to be true in this scenario is that although the limit kind of doesn't exist, this x squared term is just getting bigger. So this x squared term right here is getting bigger faster than this x to the 1 term. So what's happening is it's not that the limit doesn't exist, but as we get further and further out on our x, this polynomial is just going to skyrocket up to infinity. It's just going to tend off to infinity instead of tapering off at some point. All right, let's take a look at this next limit. This is a little bit curious one. This is another 0 divided by 0 scenario if you just plugged in x equals 3. So this limit might exist. Let's take a look. First thing that we'd want to do in this scenario is let's try and see if we can take the top part and make it non-radical anymore. We're going to sort of rationalize, it's called, the top. And how we'd accomplish this is when you have something, so when you have x squared minus 9, this equals x minus 3 times x plus 3. This is a difference of squares scenario that we can use to our advantage. So if we took root 3 minus x and multiplied it, in this case, root 3 minus x, and multiplied that by root 3 plus x, using the same sort of reasoning here, matching up each of the terms, we're going to get root 3 squared minus, oh, I forgot the root x there, minus root x squared. So this is going to be 3 minus x, which is totally rational. So let's go ahead and take this term right here. Let's take that, and we're going to multiply the top and the bottom by root 3 plus root x. And we're going to continue that down here. So equals the limit as x approaches 3 of root 3 minus root x divided by 3 minus x times root 3 plus root x over root 3 plus root x. So let's go ahead and take this right here, multiplication on top, we already established. That is going to approach root 3 squared, which is 3, minus x. We have it written down right there, 3 minus x, over, and we're just going to leave this bottom term without multiplying it through, root 3 plus root x. And what you notice is that this term up top and this term on the bottom can cancel out. And this leaves us with the limit as x approaches 3 for 1 over root 3 plus root x. Now we can take the limit as x approaches 3 because this bottom term doesn't tend to 0 anymore. And when we evaluate that, we get 1 over root 3 plus root 3 or 1 over 2 root 3. Now, for our last limit, we're going to have this one, which involves a trigonometric identity. And when you see a trigonometric identity, you can't really do as much as you'd be able to do with polynomials, as we saw before, where you know a whole bunch of tricks from algebra. What we do know to be true about sine x is we know its bounds. We know that sine x is trapped between -1 and 1. And if you're new to sort of trigonometry, basically sine x is the height of a circle of radius 1. And of course, the height can only peak at +1 up here for height and -1 down here. So the sine is just going to be trapped between this circle. So how do we take this expression, use the squeeze theorem to figure out this expression? We want to take this and figure out this. Well, all we have to do is just divide each of the terms by x. Now we know that -1 over x is less than or equal to sine x over x less than or equal to 1 over x. And now, let's just apply a limit to each of these terms. Limit x approaches infinity -1 over x less than or equal to the limit as x approaches infinity sine x over x less than or equal limit as x approaches infinity of 1 over x. And now you can see that these two edge terms are going to get closer and closer to 0. The 1 over x's approaching infinity always get closer and closer to 0. So this gives us our statement that 0 is less than or equal to the limit as x approaches infinity sine x over x less than or equal to 0. I mean, it couldn't be any more obvious. If it's between 0 and 0, using the squeeze theorem, we know that this limit has to reach 0. That gives us the other answer for this limit, giving us the limit is 0. So that's all for now on limits. I just thought I'd show you a few ways that we can evaluate limits. Next video, I promise, because I've been very elusive on this, I'm actually going to cover what the definition of the derivative is. And as always, keep on learning.